Haribode, weak acid strong base titrations, 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 (25 cubic centimeters of 0.3 moles per cubic decimeter HA solution is taken into a titration flask and it was titrated against 0.3 moles per cubic decimeter sodium hydroxide solution. So this is what you called as weak acid strong base titrations. Weak acid strong base titrations. Right? The simple Roman number 3, simple Roman number 2, simple Roman number 2. Question simple Roman number 2. Calculate the pH. Calculate the pH at equivalence point. Calculate the pH at equivalence point. Calculate the pH at equivalence point. Right? Roman number 2. Simple Roman number 2. Calculate the pH at equivalence point. Right. Then, what do you mean by equivalence point? You have weak acid. You have weak acid HA active. You have weak acid HA AQ in the titration flask. In the titration flask, and it was titrated. It was titrated against. It was titrated against a sodium hydroxide solution, a sodium hydroxide solution NaOH active, and you get sodium acetate sodium salt of acid Na active, sodium salt of acid and water as products. When a weak acid is titrated against a strong base, when a weak acid is titrated against a strong base, you get a sodium salt of the acid and water as products. Right? So, what do you mean by equivalence point? What do you mean by equivalence point? The reagent present in the titration flask, the reagent present in the titration flask is completely neutralized. That is what you called as equivalence point, right? the reagent present in the titration flask is completely neutralized. That is what you call as equivalence point. Okay. So I can calculate initial amount. I can calculate initial amount. We have taken 0.3 moles per cubic decimeter HA solution and 25 into 10 to the power minus 3 cubic decimeters from that solution. I apply N equals CV for this calculation, right? Then the amount of the weak acid present in the titration flask is 7.5 into 10 to the power minus 3 cubic, 10 to the power minus 3 moles. That is the initial amount present in the titration flask. And I can obtain the added amount. I can obtain the added amount. I can obtain the added amount if this is the equivalence point, right? If this is the equivalence point, then the added amount is equal, right? The added amount is equal to the initial amount present in the titration flask, because the stoichiometry is 1:1. And what do you mean by equivalence point? Equivalence point means whatever the reagent present in the titration flask is completely neutralized, right? Whatever the reagent present in the titration flask is completely neutralized. That is what you called as equivalence point. So the stoichiometry is 1:1. So the initial amount of HA is 7.5 into 10 to the power minus 3. Then the amount of sodium hydroxide added is exactly equal to that amount. So the added amount is 7.5 into 10 to the power minus 3 moles. That is the added amount. Okay. That is the added amount. Then I can calculate reacted amount. I can calculate reacted amount. I can calculate the reacted amount. So both have identical amounts, both have equal amounts, right? Both reagents have equal amounts, so they are completely neutralized. They are completely neutralized. So the reacted amount is 7.5 into 10 to the power minus 3 moles and 7.5 10 to the power minus 3 moles. So these are the reacted amounts. Then final amounts. Final amount. Here you have 7.5, that is the initial amount, and this is the reacted amount. Initial amount is completely neutralized from the added amount or the reacted amount. From the added amount, that means the reacted amount is equal to the added amount, to the initial amount. So this is your initial amount, this is your reacted amount. No remaining amount of HA. No remaining amount of HA. And this is the added amount and this is the reacted amount. No remaining amount of sodium hydroxide. But it is 1:1:1 stoichiometry. It it is 1:1:1 stoichiometry. So you get same amount of sodium salt of acid, you get same amount of sodium salt of acid, because it is equivalence point. Okay, same amount, because the stoichiometry is 1:1. Stoichiometry is 1:1. So the reacted amount is exactly equal to the amount of sodium salt produced. Right? The reacted amount is exactly equal to the amount of sodium salt is produced. So this is how you calculate, right? This is how you should identify different species present in the equivalence point, right? This is how you should identify the different species present in the equivalence point, right? Hari අරපද මෙහෙම ලියා ගන්න. The equivalence point, in the equivalence point, the weak acid present in the titration flask, the weak acid present in the titration flask, the weak acid present in the titration flask is completely neutralized. The weak acid present in the titration flask is completely neutralized. The chemical species present in the equivalence point, the chemical species present in the equivalence point, the chemical species present in the equivalence point, the chemical species present in the equivalence point is the sodium salt of weak acid. Is the sodium salt of weak acid. Therefore, pH of the solution, therefore pH of the solution Therefore, pH of the solution is determined by pH of the solution is determined by the salt present in the titration flask. The salt present in the titration flask. Therefore, concentration of the salt has to be calculated. Therefore, concentration of the salt has to be calculated. Right. We can calculate the concentration of the salt, right? Sodium salt of weak acid, NaAQ concentration equal the amount present in the titration flask is 7.5 into 10 to the power minus 3 cubic, 10 to the power minus 3 moles, 10 to the power minus 3 moles, and the initial I use C equals N over V to calculate the salt concentration. The amount present in the titration flask is 7.5 into 10 to the power minus 3 moles. The initial volume present in the titration flask, is 25 cubic centimeters, and the volume added has to be calculated, added volume, right? Added volume. So how do you calculate the added volume? Added volume from NaOH. How do you calculate the added volume from NaOH? C equals N over V, V equals N over C. So I can calculate the volume added, because 7.5 into 10 to the power minus 3 is the amount of sodium hydroxide added. 7.5 into 10 to the power minus 3 moles. 7.5 into 10 to the power minus 3 moles, that is the amount of sodium hydroxide added. And what is the concentration of sodium hydroxide added? That is 0.3 moles per cubic decimeter. So simplify this, you get 25 into 10 to the power minus 3 cubic decimeters equal 25 cubic centimeters. So this is the volume added from the sodium hydroxide solution. Okay, that is the volume added from sodium hydroxide solution. So the volume added from sodium hydroxide solution is 25 cubic centimeters. So I should convert the unit into cubic decimeters. So multiplied by 10 to the power minus 3 cubic decimeters. 10 to the power minus 3 cubic decimeters. 25 plus 25, that is 50. 7.5 divided by 50. 7.5 divided by 50. So that is 0.3 divided by 2. That means 0.15 into 10 to the power minus 3. 10 to the minus 3, 10 to the minus 3 cancel out. So 0.15 moles per cubic decimeters, that is the concentration of the salt. Right, put the calculation එක කරගන්න. කැල්කියුලේෂන් එක කරගන්න. හරි පුතේ මෙහෙම ලියා ගන්න. To calculate the concentration of sodium salt of acid, to calculate the concentration of sodium salt of acid, the volume added from the burette, the volume added from the burette, the volume added from the burette has to be calculated. The volume added from the burette has to be calculated. Volume added from the burette has to be calculated. Because in the calculation of salt concentration, in the calculation of salt concentration, in the calculation of salt concentration, total volume present in the titration flask, total volume present in the titration flask should be considered. Total volume has to be considered, right? Now we can calculate, right? We have calculated the concentration of the salt. We have calculated the concentration of the salt. So in the titration flask, you have sodium salt of acid in the titration flask. Haribode. So, sodium salt of weak acid or whatever the sodium salt exists as dissociated ions in their aqueous solutions, right? Whatever the salt exists as dissociated ions in their aqueous solutions, right? So whatever the ions exist as whatever the sodium salt exists as dissociated ions in their aqueous solution. If the concentration of salt is 0.15 moles per cubic decimeters, concentration of sodium cation 0.15 moles per cubic decimeter and 0.15 moles per cubic decimeters. So whatever the sodium salt exists as completely dissociated ions, whatever the sodium salt exists as completely dissociated ions in their aqueous solutions, right? Whatever the sodium salt exists as completely dissociated ions in their aqueous solutions, right? Then sodium ion is a cation derived from strong base, and A minus ion, that is the anion of weak acid, so it is derived from a weak acid. A cation derived from a strong base, doesn't further hydrolyze in water. It doesn't further hydrolyze in water, but an anion derived from a weak base, right? A cation derived from a strong base doesn't further hydrolyze in water, and an anion derived from a weak acid further hydrolyze in water. Okay. Further hydrolyze in water. So the pH of the equivalence point, right? The pH of the equivalence point of weak acid strong base titration is affected by salt hydrolysis. pH of the equivalence point of a weak acid strong base titration is affected by salt hydrolysis. Okay. Right. Putih may nga piliagamu. right පුතේ මේව ලියා ගන්න. Every sodium salt exists in aqueous solutions. Every sodium salts exist in aqueous solutions as completely dissociated ions. As completely dissociated ions. Every sodium salts in aqueous solutions, every sodium salts in aqueous solution exist as completely dissociated ions. Exist as completely dissociated ions. හරි පුතේ මේම ලියා ගන්න වෙනම ලියන්න. Na plus AQ is a cation. Na plus AQ is a cation derived from Na plus AQ is a cation derived from a strong base. Na plus cation Na plus AQ cation, Na plus AQ is a cation derived from a strong base, a cation derived from a strong base, full stop. Cations derived from a strong base, cations derived from a strong base, cation derived from a strong base, a cation derived from a strong base doesn't hydrolyze in water. A cation derived from a strong base doesn't hydrolyze in water. හරි පුතේ වෙනම ලියන්න. A minus AQ is an anion. A minus AQ is an anion derived from a weak acid. A minus AQ is an anion derived from a weak acid. Derived from a weak acid. Derived from a weak acid. Full stop. Anions derived from weak acids. Anions derived from weak acids. anions derived from weak acid hydrolyze in water. Anions derived from weak acid hydrolyze in water. Anions derived from weak acid hydrolyze in water. An anion derived from a weak acid hydrolyze in water. Right. So here you have an anion derived from weak acid. Anion derived from a weak acid, that is A minus, hydrolyze in water. A minus AQ plus water H2O liquid hydrolyze in water by producing an equilibrium system, right? An anion derived from a weak acid, an anion derived from a weak acid hydrolyze in water by producing an equilibrium system. By producing an equilibrium system. So here you have A minus, it is negatively charged ion, it is negatively charged ion, it should accept a positively charged cation, right? Here A minus, it's a negatively charged ion, it's a negatively charged ion, it accepts a proton, it should accept a positively charged cation, it should accept a positively charged cation from water because this is negative, it should accept the opposite charge cation. So in water you have H pluses, in water you have H pluses, so A minus accept H plus, A minus accept H plus by producing HA. By producing HA. By producing HA. In water you have H plus and OH minus, right? In water you have H plus and OH minus. A minus accept H plus from water and produce HAAQ and OH minus. Right? And OH minus. A minus, it's a negatively charged ion, accept H plus. So you get HA. The remainder is OH minus. Okay? So now you can understand. Here you have hydroxide ions. Here you have hydroxide ions. If you can calculate hydroxide ion solutions, hydroxide ions present in the solution, hydroxide ion concentration present in the solution, then you can calculate the pH, right? If you can calculate hydroxide ions present in the solution, right? Hydroxide ion concentration present in the solution, then you can calculate pH, right? So this is the hydrolysis of weak acid anion in aqueous solution, right? This is the hydrolysis of weak acid anion in aqueous solution, right? right පුතේ ලියන්න මේ ඉක්විලිබ්‍රියම් එක. හරි පුතේ මේම ලියා ගන්න. weak acid anion accept H plus. Weak acid anions accept H plus from H2O liquid in an aqueous solution. Weak acid anions, right? Weak acid anions accept H plus from H2O liquid in an aqueous solution. The resulted solution consists with OH minus AQ. The resulted solution consists with OH minus AQ. The resulted solution consists with OH minus AQ. And OH minus AQ concentration has to be calculated. OH minus AQ concentration has to be calculated. OH minus AQ concentration has to be calculated. In order to calculate pH of the solution. in order to calculate pH of the solution. Okay, right. To calculate OH minus AQ concentration, to calculate OH minus AQ concentration, to calculate OH minus concentration, to calculate OH minus concentration, OH minus AQ concentration, the equilibrium constant of the above equilibrium, the equilibrium constant of the above equilibrium, the equilibrium constant of the above equilibrium has to be calculated. The equilibrium constant of the above equilibrium has to be calculated. Of the above equilibrium has to be calculated, right? To calculate the hydroxide ion concentration, the equilibrium constant for this equilibrium has to be calculated, right? Because what is the equilibrium constant for this? Equilibrium constant K equal concentration of HAAQ into hydroxide ion concentration divided by A minus concentration into H2O liquid concentration. H2O liquid concentration is always a constant. H2O liquid concentration is always a constant at constant temperature. H2O liquid concentration is always a constant at constant temperature. Therefore, it has to be taken into your left hand side, right? It has to be taken into the left hand side of the equation. So you get K H2O liquid into HAAQ concentration into OH minus concentration divided by A minus concentration, right? A minus concentration. Equilibrium constant and H2O liquid concentration also a constant. So the multiplication of these two also a constant. That is what you called as KB for this equilibrium constant, for this equilibrium. KB for this equilibrium. Why B? B stands for base. B stands for base. B stands for base, right? So here you have hydroxide ion concentration. Here you have hydroxide ions. So it is a basic equilibrium, right? hydroxide ions are resulted, hydroxide ions are resulted, hydroxide ions are resulted, therefore it is a basic equilibrium. So the equilibrium constant for this equilibrium constant for this basic equilibrium is known as Kb, right? B stands for base. Therefore, equilibrium constant for this equilibrium is Kb equal HAAQ concentration, HAAQ concentration into hydroxide ions concentration divided by A minus AQ concentration. A minus AQ concentration. So this is the equilibrium constant. This is the equilibrium constant equation. This is the equilibrium constant equation for this equilibrium. Right. පුතේ ඔය වෙනකන් ලියාගමු. ඔය වෙනකන් ලියාගමු. හරි පුතේ. Then you have equilibrium constant equation here. This is how you derive this equation, right? This is how you derive this equation. You don't need to derive this equation in an exam. You directly take this equation, right? Kb. So you have Kb so I can write Kb here. Kb equal HAQ concentration into OH minus concentration divided by A minus concentration, right? පුතේ පොඩ මෙහෙම ලියාගමු. The above equilibrium equation, the above equilibrium solution, the above equilibrium solution the above equilibrium solution consist with OH minus AQ, 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 ions, consist with OH minus AQ ions, and it is a basic solution, and it is a basic solution. The equilibrium constant, for these kind of basic solutions, the equilibrium constant for these kind of basic solutions the equilibrium constant for these kind of basic solutions is known as KB, is known as KB, is known as KB. Right. So even the equilibrium constant for this basic solution is KB. It is not given as a data in the calculation, right? Because this is a weak acid strong base titration, right? This is a weak acid strong base titration. This is a weak acid strong base titration. So in a weak acid strong base titration, it is always, right, in a weak acid strong base titration, always only the dissociation constant for the acid, right, dissociation constant for the acid is given, right. So in the beginning of this titration, I have given Ka, which is acidic dissociation constant of Ha. Acidic dissociation constant of Ha is 1 into 10 to the power minus 5 moles per cubic decimeters. If your titration is a weak acid strong base titration, right? If your titration is a weak acid strong base titration, you are not given Kb for its anion, right? You are not given Kb for its anion. For weak acid strong base titration, always the acidic dissociation of HAAQ is given, right? For weak acid strong base titration, always the acidic dissociation constant Ka of Ha is given, right? Right. Puteliana. In a weak acid strong base titration, 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 acidic dissociation constant, the acidic dissociation constant within brackets Ka, within brackets Ka of HAAQ, of HAAQ, of HAAQ is always given. 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 minus AQ, KB of A minus AQ, KB of A minus AQ is not given. KB of A minus AQ, KB of A minus AQ is not given. 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 It has to be calculated. It has to be calculated. Right. To calculate KB, right? To calculate KB, you can use this relationship KA into KB equal KW, right? KA into KB equal KW. That is the relationship you use to calculate KB, because KA is given in the question and KW is always given, so you can calculate KB, right? You can calculate KB. To calculate KB, the following equation can be used. To calculate KB, the following equation can be used. To calculate KB, the following equation can be used. Right. Putih liagan මේක. හරි පුතේ. මේව ලියන්න. It can be proved as follows. It can be proved as follows. මේ equation එක අපි prove කරනවා. මේ equation එක අපි prove කරනවා මෙන්න මේ විදියට. Right? So this is A minus AQ and that is KB for this equilibrium, right? A minus AQ is in equilibrium in aqueous solution, and I consider HAAQ dissociate as H plus AQ and A minus AQ, right? HA is the weak acid, right? HA is the weak acid and A minus is its anion, right? HA is the weak acid and A minus is its anion, and we call that as conjugate acid base pair. HA is a weak acid and A minus is its anion, right? And you call that as conjugate acid base pair. Conjugate acid base pair, right? You call that as conjugate acid base pair, right? You call that as conjugate acid base pair. Okay. So HAAQ is the weak acid, HAAQ is the weak acid, and A minus AQ is its conjugate base. Conjugate base. HA is the weak acid and A minus is its conjugate base. A minus is a weak base and HA is its conjugate acid. Okay. HA is a weak acid and A minus is its conjugate base. A minus is a weak base and HAAQ is its conjugate acid, right? Conjugate. So HA is a weak acid and A minus is its conjugate base. A minus is a base and HA is its conjugate acid. Okay. Right. For this equilibrium, this is the equilibrium equation. Okay. And for this equilibrium, I can write the equilibrium equation, that is Ka equal, because it is acidic dissociation. It is acidic dissociation. So you have H pluses. You have H pluses. So it is Ka. It is Ka. It is an acidic dissociation. It is Ka. So H plus AQ. H plus AQ into A minus AQ. H plus AQ into A minus AQ, H plus AQ into A minus AQ divided by HAAQ. Divided by HAAQ. H plus AQ into A minus AQ divided by HAAQ. So, Kb is the acidic dissociation constant. Sorry, Kb is the basic dissociation constant of A minus, and Ka is the acidic dissociation constant of Ha. Ha and A minus is the conjugate acid base pair, right? Ha and A minus is the conjugate acid base pair. For conjugate acid base pair, right? For conjugate acid base pair, Ka into Kb equals Kw, right? For conjugate acid base pair, Ka into Kb equal Kw. ඒ කියන්නේ Ka into Kb equal Kw කියන equation එක you can apply for any acid base pair, right? You can apply only for a weak acid and its conjugate base, right? Weak acid and its conjugate base, which is known as acid base conjugate pair, right? Acid base conjugate pair. It cannot be applied for any mixture, right? Any mixture, right? You cannot apply that for any pair of acid bases, right? Any pair of acid and base. It can be applied for only conjugate acid base pair, which means the weak acid and its conjugate base and weak base and its conjugate acid. Okay, you can apply for that kind of situations, right? Okay, so for these two equilibriums, you write these equilibrium constants, and our equation is Ka into Kb equals Kw, right? Our equation is Ka into Kb equal Kw. What is it mean? Ka into Kb, right? You multiply Ka and Kb. So left hand side of equations, Ka into Kb, right? It's better you write Ka of HAAQ into Kb of A minus AQ. Kb of A minus AQ, right? A minus AQ. Okay, it's better. Right, Ka into Kb equal what? Ka multiplied by Kb means this whole thing, right? This whole thing is multiplied by this thing. Okay. So here you have H plus here. Sorry. Here you have HAAQ, right? Here you have HAAQ in numerator, and here you have HAAQ in denominator. So multiplication of these two equations, which means Ka into Kb in the left hand side, means this thing is multiplied by this thing. So here HAAQ is in the numerator, here it is in the denominator, so it will be cancelled out, and here A minus is in the denominator and here it is in the numerator, it will be cancelled out. So finally you get H plus AQ into OH minus AQ. So finally you get H plus AQ into OH minus AQ. So in the previous question I have explained H plus AQ into OH minus AQ means H plus AQ into OH minus AQ means that is Kw. So Ka into Kb equal Kw. Okay, Ka into Kb equal Kw. This is how you prove that equation, right? It is easy to prove. It is easy to prove. Okay? Right. පුතේ මේක ලියා ගන්න. First මේ equilibrium එක ලියා ගන්න. Second මේ equilibrium එක ලියා ගන්න. Third එකට it's better you can write this equilibrium, this equation. Fourth එකට මේ equation එක. Fifth එකට මෙයා ලියා ගන්න. Sixth එකට මෙයා ලියා ගන්න. That's the best method, right? Best sequence. Right. Best sequence එකට ලියා ගන්න, right? Okay. Haribute. Now we have we should calculate we should calculate we should calculate OH minus AQ concentration, right? We should calculate OH minus AQ concentration, right? You should calculate OH minus AQ concentration. You should calculate OH minus AQ concentration. You should calculate OH minus AQ concentration, right? So now we have the equilibrium constant Kb equal HAAQ into OH minus AQ concentration, HAAQ into OH minus AQ concentration divided by A minus concentration, that is your Kb, right? Now you have that. So now you can understand, you can calculate a hydroxide ion concentration, right? You can calculate hydroxide ion concentration if you have the concentration of A minus, right? If you have the concentration of A minus, because we have the initial concentration of A minus. We have the initial concentration of A minus. We have the initial concentration of A minus. Initial concentration. We have the initial concentration. It is A minus concentration is 0.15 moles per cubic decimeters. It is 0.15 moles per cubic decimeters, and when the system is reached for the equilibrium, I can consider change in concentration as minus X. I can consider change in concentration as minus X, which means you have 0.15 as the initial concentration. X amount of A minus is dissociated, right? X amount of A minus AQ is dissociated, right? Initially you have 0.15 moles per cubic decimeter concentration, and when the system is reached for equilibrium, I can consider X moles per cubic decimeter X moles per cubic decimeter A minus AQ concentration is changed. That is the change. For example, say you have 100 moles of A minus AQ, right? You have 100 moles of A minus AQ, and when the system reached for the equilibrium, now you have 99 moles of A minus AQ, right? Initially you have 100 moles of A minus AQ, and when the system reached for the equilibrium, now you have 99 moles of A minus AQ, right? 99 moles of A minus AQ. So what is the change? 99 minus 100. So the minus 1 is the change. Okay, minus 1 is the change. So likewise, if the initial concentration of A minus is 0.15, you can consider minus x as the change of A minus concentration. Minus x is the change of A minus concentration. If minus x is the change of A minus concentration, 1:1 stoichiometry, 1:1 stoichiometry, you get plus x of HAAQ, you get plus x of HAAQ, and you get plus x of OH minus AQ. It's like 100 moles of A minus is there. Change of A minus is 1 mole, and it is converted into 1 mole of HA and 1 mole of OH minus. For example, mage 100ක් මෙතන ඉන්නවා, මං වගේ 100ක් ඉන්නවා, right? මං වගේ 100ක් ඉන්නවා, and complete, right? and එයා dissociate වෙනවා දෙන්නෙක්ට. ඒ කියන්නේ මගේ හිස කඳින් වෙන් වෙනවා, මගේ හිස කඳින් වෙන් වෙනවා. එතකොට හිස කඳින් වෙන් වෙනකොට HA, that is කියන්නේ හිස රහිත කඳ, right? HA කියන්නේ හිස රහිත කඳ, OH minus කියලා කියන්නේ හිස. මේ තියෙන්නේ සම්පූර්ණ මම. සම්පූර්ණ මගෙන් 100ක් ඉන්නවා, සම්පූර්ණ මගෙන් 100ක් ඉන්නවා. එයාගෙන් එක්කෙනෙක්ගේ හිස කඳින් වෙන් වෙනවා, එයාගෙන් එක්කෙනෙක්ගේ හිස කඳින් වෙන් වෙනවා. එහෙනම් මේ තියෙන්නේ හිස රහිත මම, මේ ඉන්නේ මගේ හිස. හරිනේ? එතකොට so අන මගෙන් එක්කෙනෙක්ගේ හිස කඳින් වෙන් වුණාම හිස රහිත මගෙන් එක්කෙනෙක් එනවා, ඒ වගේම මගේ හිස එනවා. පැහැදිලි නේ කියන දේ? So that is what you call as stoichiometry. It is 1:1:1. So initial concentration 0.15 moles per cubic decimeter, initial concentration 0.15 moles per cubic decimeter, the change is minus x, the change is minus x, and HAAQ plus x, OH minus AQ plus x. Okay? Okay, right? So I can calculate the equilibrium concentration. This is the change. Then I can calculate equilibrium concentration. Equilibrium concentration. Equilibrium concentration 0.15 minus x, 0.15 minus x, 0.15 minus x, and you get x, right? 0.15 minus x, you get x, 0 get x, right? So this is your equilibrium concentration. Equilibrium concentration, right? So if you can calculate the value of x, if you can calculate the value of x, then you can calculate, if you can calculate the value of x, then you can calculate concentration of hydroxide ions. To calculate the value of x, the only, right, to calculate the value of x, you can apply equilibrium equation. Okay, you can apply equilibrium constant equation to calculate x, right? පුතේ ඔය වෙනකන් අපි ලියාගමු. ඔය වෙනකන් ලියාගමු. you can calculate the value of X to calculate hydroxide ion concentration, right? You can calculate the value of X in order to calculate the concentration of hydroxide ions. In order to calculate the concentration of hydroxide ions. In order to calculate the concentration of hydroxide ions, right? So, Kb equal A minus AQ with H2O liquid, you get HAAQ plus OH minus AQ, right? So Kb equal HAAQ concentration into OH minus AQ concentration divided by A minus AQ concentration. So you have these concentrations in the equilibrium equation. So Kb is Kw over Ka, because I have explained Ka into Kb equals Kw. So that is your equation, Ka into Kb equal Kw, that is your equation. So Kb equal Kw over Ka, right? Kb equal Kw over Ka equal HAAQ concentration. I have explained X moles per cubic decimeter, and OH minus concentration is X moles per cubic decimeter, and the unit is moles per cubic decimeter squared, because here you have moles per cubic decimeter and here you have moles per cubic decimeter. So this is moles per cubic decimeter squared, right? Then A minus concentration is 0.15 minus X, 0.15 minus X moles per cubic decimeter, right? Moles per cubic decimeter. So you can further simplify. Kw is 1 into 10 to the power minus 14 moles per cubic decimeter squared. Kw is always given in a question. Kw is always given in a question. It is 1 into 10 to the power minus 14 moles per cubic decimeter squared at 298 Kelvin, right? It is 1 into 10 to the power minus 14. It is 1 into 10 to the power minus 14 moles per cubic decimeter squared at 298 Kelvin. At 298 Kelvin, right? Divided by Ka equal, it is given 1 into 10 to the power minus 5 moles per cubic decimeter, 1 into 10 to the power minus 5 moles per cubic decimeter equal X squared over 0.15 minus X, 0.15 minus X, right? 0.15 minus X. So you can understand 1 into 10 to the power 10 to the power minus 5, 10 to the power minus 14. So you get 10 to the power minus 9, right? 10 to the power minus 5 cancel out with 10 to the power minus 14. So you get 10 to the power minus 9 equal x squared over 0.15 minus x. And this equilibrium constant is a much smaller value. This equilibrium constant is a much smaller value, that is 10 to the power minus 9, and I have explained that in the previous question. At that kind of situation, you can consider that 0.15, you can consider that 0.15 x is much smaller when compared with the 0.15. If the equilibrium constant is a much smaller value, if the equilibrium constant is a much smaller value, you can consider that x is much smaller than 0.15, therefore 0.15 minus x approximately equal to 0.15, right? 0.15 minus x is approximately equal to 0.15. Okay, so I can go further simplification. I can go for further simplification. 1 into 10 to the power minus 9 equal x squared over 0.15. So x squared equal 1.5 into 10 to the power minus 10, x equal 1.5 into 10 to the power minus 5. Right. Putih, ඔය වෙනකන් simplification එක කරගමු.